Light obeys a law unlike any other. It travels at a constant speed, a universal limit governing everything from the faintest radio whisper to the most energetic gamma-ray burst. This constancy is not merely a scientific observation. It is the foundation upon which we perceive reality. Light moves in straight lines, or so scientists believed for centuries. Were this not true, the world would dissolve into an indistinct haze, rendering comprehension impossible. For millennia, this assumption underpinned all understanding of optics and vision. Yet, even before the 20th century, theory hinted at a more intricate truth. Calculations rooted in Newton's theory of universal gravitation suggested that massive objects should deflect light, bending its trajectory. This was a startling concept, implying that light, despite possessing no mass, might be susceptible to gravitational influence. The deflection predicted by Newtonian physics was tiny, however, and the technology required to measure it lay decades away. The question would remain open until astronomers could compare star positions during the rare moment when the sun's blinding glare was obscured. Our intuitive grasp of motion stems from everyday experience. We perceive gravity as a force drawing objects downward. However, gravity is remarkably weak. It requires the entire mass of Earth to keep our feet firmly planted on the ground. Detecting its influence on something traveling at the speed of light demands an object of immense mass, coupled with exceptionally precise measurement. The solar eclipse of 1919 provided precisely such an opportunity. Astronomers journeyed to remote locations in Brazil and West Africa to photograph stars positioned near the eclipsed sun. The results showed that starlight passing close to the sun was indeed bent. But the deflection they measured was twice what Newton's theory predicted. It matched, instead, the strange new theory of a relatively unknown German physicist. What if gravity is not a force acting upon light, but rather a warping of the very fabric of space through which light propagates? What if light always travels in a straight line, while space itself is curved? This is the question Albert Einstein confronted, and his answer would irrevocably alter our understanding of the cosmos. A single planet defied the most successful theory in history. For over 2 centuries, the motions of the planets were understood through a force, gravity. Isaac Newton's law of universal gravitation stated that every particle of matter in the universe attracts every other particle. The greater the mass, the greater the pull. And the closer the objects, the more intense the interaction. This was an idea of remarkable power. With this law, Newton could predict the future positions of the planets with unprecedented accuracy. He explained the falling apple and the moon's orbit. He even accounted for the subtle wobble in Earth's axis, caused by the sun's gravitational influence. It appeared complete. It appeared definitive. And for a time, it was sufficient. However, the universe rarely yields to neat, complete answers. As astronomical observations became more refined, subtle discrepancies began to emerge. Closest to the Sun, the planet Mercury did not follow the path predicted by Newtonian gravity. Its orbit traced a slow, creeping ellipse that did not quite close completely. Each time Mercury circled the Sun, its closest approach shifted slightly. A small amount, certainly, but measurable. And it defied explanation. Scientists proposed numerous solutions. Perhaps an undiscovered planet orbited even closer to the Sun than Mercury. This hypothetical world received a name, Vulcan. Teams of astronomers scoured the space between Mercury and the Sun, dedicating years to the search. They believed Vulcan's gravity was distorting Mercury's orbit. Many considered its discovery possible. Dedicated observers meticulously charted the Sun's surface, searching for any sign of this hidden world. They sought the telltale wobble in the Sun's position caused by Vulcan's gravitational influence. Instruments were improved. Techniques were refined. Years turned into decades. The search continued. Yet Vulcan remained elusive. No planet was found. No evidence emerged. The discrepancy in Mercury's orbit persisted. It was as if the universe was whispering a secret, hinting that the explanation lay beyond Newtonian physics. The search for Vulcan ultimately failed. It was not a matter of better telescopes or more diligent observation. The problem was not a missing planet. Something more fundamental was at play. The very framework for understanding gravity itself needed to be re-examined. But what if the force we thought we understood was not a force at all, but a symptom of something far stranger? The universe presents a contradiction. Objects fall, yet there is no discernible hand to push them. For centuries, we believed space and time were immutable, a static arena for cosmic events. But what if that arena itself is dynamic? What if space and time are not separate entities, but interwoven into a single, unified fabric we call spacetime? 4 dimensions, 3 of space and 1 of time, are not merely a backdrop, but a malleable entity. Mass and energy sculpt this fabric. A small object creates a subtle distortion, while a star, possessing immense mass, generates a significant curvature. A black hole, with its almost incomprehensible density, forms a well from which nothing, not even light, can escape. Objects do not travel through space-time, they travel along with it. They follow the contours shaped by the distribution of mass and energy. We experience this as gravity. It is not a force exerting a pull, but the natural consequence of moving along the curves of spacetime. Reflect on the sensation of acceleration. The force pressing you into your seat during rocket ignition feels identical to the familiar pull of gravity. This is not accidental. Albert Einstein recognized a fundamental truth: gravity and acceleration are indistinguishable. This is the equivalence principle. A person within a sealed elevator cannot determine whether they are stationary on Earth or accelerating upwards in the void. This deceptively simple insight triggered a revolution in our understanding. It revealed that gravity is not a force, but a manifestation of spacetime's geometry. Light, too, must adhere to these curves. Though possessing no mass, light carries energy, and energy, like mass, warps the fabric of spacetime. If spacetime bends to the will of mass, then light itself must follow these distorted paths. This leads to a consequence that defied previous conceptions. A consequence that would have remained hidden without Einstein's radical perspective. Light does not travel in straight lines. During a total solar eclipse, the sun's disk vanishes behind the moon, but this is no ordinary darkening. It is a fleeting glimpse beyond our everyday reality. Stars normally overwhelmed by the sun's brilliance emerge, painting a black canvas with distant fire. For a few precious minutes, we possess the opportunity to investigate the foundations of gravity. Einstein proposed that massive objects do not simply exert a force, but rather warp the fabric of spacetime itself. Light, always following the shortest path, travels along these curves, appearing to bend as it passes near a massive body. The Sun, possessing immense mass, is predicted to deflect starlight. The deviation would be slight, less than 2 arcseconds, an angle so small that detecting it required photographing stars whose light had grazed the Sun itself. To verify this prediction, expeditions were essential. 2 teams of British astronomers traveled to opposite sides of the Atlantic. One, led by Arthur Eddington, journeyed to the island of Principe off the coast of West Africa. The other traveled to Sobral in northern Brazil. It was a considerable risk. The world was still recovering from the First World War. International collaboration was difficult, and the weather at both locations was notoriously unpredictable. The astronomers photographed the stars near the eclipsed Sun. These images were then compared with photographs of the same stars taken simultaneously under normal night sky conditions. If Einstein's theory held true, the positions of the stars near the Sun would appear shifted, bent ever so slightly by the Sun's gravitational influence. The initial results proved inconclusive. Cloud cover hampered observations. The equipment was rudimentary by modern standards. However, after meticulous analysis, the data appeared to corroborate Einstein's prediction. The starlight had demonstrably bent. General relativity was not simply an elegant theory. It appeared to be a correct description of reality. The news resonated globally. A relatively unknown German physicist had overturned 3 centuries of Newtonian physics. This was a paradigm shift. Gravity was no longer a force pulling on objects, but the curvature of spacetime. And light, that seemingly weightless entity, followed this curvature as predictably as any planet or asteroid. The confirmation of general relativity fundamentally altered our understanding of the universe. It laid the groundwork for countless discoveries that followed, from the expansion of the universe to the existence of black holes. It was a moment when the course of science itself irrevocably changed. But the bending of light is not merely a subtle effect observable during eclipses. It becomes extreme in the vicinity of the most massive objects in the universe, places where gravity is not merely strong, but all-consuming. Places where even light itself can be captured, unable to escape. A black hole is not a cosmic vacuum cleaner, relentlessly sucking up everything around it. It is a region where the curvature of spacetime becomes infinite. A place where gravity's influence is not a pull, but the very shape of reality itself. To understand this, we must first consider how these objects form. Most begin their lives as massive stars. Stars far larger than our Sun. They burn brightly, furiously, for millions of years. But even their immense fuel supply is finite. When a star exhausts its nuclear fuel, the outward pressure that held it aloft against its own gravity weakens. The core collapses. It implodes. For smaller stars, this collapse is halted by the pressure of electrons or neutrons. They become white dwarfs or neutron stars, incredibly dense but still finite objects. But for the most massive stars, there is no such reprieve. Gravity overwhelms everything. The core collapses endlessly, crushing matter into a singularity, a point of infinite density. Around this singularity, lies the event horizon. A boundary, a point of no return. It is not a physical surface, but a region of space-time beyond which nothing, not even light, has the escape velocity to overcome the gravity. Cross it and you are lost to the outside universe. The event horizon's size depends on the black hole's mass. The more massive the black hole, the larger the event horizon. These stellar black holes, the remnants of individual stars, are scattered throughout galaxies. But some black holes are far more immense. Supermassive black holes reside at the centers of most, if not all, galaxies. Ours, at the center of the Milky Way, contains millions of times the mass of our Sun. Their origins are still a matter of ongoing research, but they likely grew over billions of years, consuming gas, dust, and even other stars. The intense gravity around a supermassive black hole sculpts the orbits of stars, influencing the very structure of the galaxy itself. It is a paradox. Something that destroys light and matter also gives birth to the swirling patterns of galactic arms and the brilliant glow of galactic nuclei. These objects, these singularities wrapped in event horizons, represent the ultimate triumph of gravity, a place where the known laws of physics break down, where spacetime is warped beyond recognition. As light approaches a black hole, its path becomes increasingly distorted. It bends, stretches, and slows. But what happens when light gets close enough? What happens when it reaches a point where it no longer falls toward the black hole, but around it? A simple experiment reveals a profound truth. There is a velocity at which an object will not fall back to Earth, but instead orbit. Increase the force of the throw, and the arc widens, the descent slows. At a critical speed, the object curves with the planet, perpetually falling without ever landing. Light possesses no mass, yet it too follows the contours of spacetime. Around a black hole, these contours become impossibly steep. At a specific distance from the event horizon, light's descent ceases. It enters a region where spacetime is so severely warped that photons can orbit, defining a boundary known as the photon sphere. This is not a solid surface, nor a physical barrier. It is a region sculpted by gravity. Current models suggest the photon sphere's radius is approximately 1.5 times that of the event horizon. A photon entering this sphere does not travel in a perfect circle, but rather spirals inward or outward, constantly influenced by the black hole's inexorable gravity. These orbits are inherently unstable. Even the slightest disturbance, a stray photon, a ripple in spacetime, can deflect a photon from its course. A minor push sends it spiraling inward, crossing the event horizon. A gentle pull allows it to escape into the cosmos. A truly stable orbit remains a mathematical ideal, seldom realized in the turbulent reality of space. Time itself undergoes a dramatic transformation within the photon sphere. The intense gravity causes extreme time dilation. To an outside observer, light orbiting within this region appears frozen, stretched, and smeared into a luminous ring. A photon completing even a single orbit would seem to require an infinite duration. This is not merely a trick of perception. Time genuinely passes more slowly within such a powerful gravitational field. Should one somehow withstand the crushing tidal forces and observe a clock within the photon sphere, it would appear to tick noticeably slower than one's own. The closer the clock approaches the event horizon below, the more dramatic the disparity becomes, until time from the outside appears to halt entirely. The photon sphere is not simply a theoretical prediction arising from Einstein's equations. It directly influences how we observe black holes. The brilliant ring of light seen in images from the Event Horizon Telescope is, in part, a consequence of photons trapped within this region, bent and amplified by the black hole's gravity. The dark silhouette at the center is not the black hole itself, but a shadow cast by light endlessly circling the abyss. But if light can orbit a black hole, and time itself bends to its will, what other fundamental constants might be redefined at the edge of oblivion? A black hole does not simply consume light, it reshapes it. It is not a void, but a region where gravity bends and amplifies photons, creating a darkness born of distortion, a silhouette cast by the space surrounding it, not the black hole itself. The event horizon represents the ultimate boundary. Beyond this point, escape is generally considered impossible. However, the shadow we detect extends beyond the event horizon, a consequence of the photon sphere. Within this region, light can orbit the black hole, held in a gravitational dance. Photons entering at a precise angle will circle once, twice, and potentially endlessly before either escaping or succumbing to the pull. This orbital behavior generates a ring of light, a warped and magnified image of the material within the accretion disk. Light originating from the far side of the disk, normally obscured, is bent around the black hole, increasing the apparent brightness and size of the entire structure. It is a cosmic lens, sculpted by the force of gravity. The shadow's size correlates with the black hole's mass. Greater mass generally yields a larger shadow due to more severe light bending. The shadow's edge is not perfectly sharp. Photons grazing closer to the photon sphere are bent more steeply than those passing further out, blurring the boundary into a smooth gradient between absolute darkness and the brilliant ring of light surrounding it. Capturing this subtle effect demanded an instrument of unprecedented precision. The Event Horizon Telescope is not a single entity, but a global network of radio telescopes. By combining their signals, it creates an Earth-sized aperture, achieving the necessary resolution to discern a black hole's shadow. The first image, depicting the supermassive black hole at the center of the Messier 87 galaxy, was a triumph of engineering and a validation of Einstein's theories. That image was more than a photograph. It was a confirmation of our understanding of gravity. It demonstrates that light, like matter does, obeys the curvature of spacetime. The darkness is not emptiness, but a visual representation of this curvature, a glimpse into the fundamental fabric of reality. The photon sphere is not merely a visual phenomenon. The shadow's shape encodes the geometry of the spacetime around it. Subtle distortions in the ring tell us about the black hole's mass, its spin, and the warping of space in its immediate vicinity. But the question of what happens to information that crosses the event horizon, of whether anything can ever truly return from beyond, remains one of the deepest unresolved puzzles in modern physics. Gravity does not merely pull objects together, it distorts the very structure of space and time. A sufficiently massive object, such as a galaxy cluster, creates a depression in this fabric, altering the paths of everything that passes nearby. Light, though without mass, is not exempt from this influence. This bending of light is gravitational lensing. Initially, the effect is subtle, a delicate warping of distant starlight. However, when a distant source, a massive object, and we are precisely aligned, the effect intensifies. Light bends, stretches, and multiplies, presenting us with multiple images of the same distant object. These are not mere reflections, but ghostly echoes of the original source, refracted by the curvature of space. Should a distant galaxy align perfectly behind a massive object, the light does not split into multiple images. Instead, it bends into a complete circle, an ethereal ring surrounding the lensing object. This is an Einstein ring, a breathtaking demonstration of gravity's power to sculpt light itself. More often, alignments are imperfect. We observe arcs, fragments of these rings stretched and distorted by the uneven distribution of mass within the lensing object. Even these arcs are invaluable. They function as cosmic telescopes, revealing galaxies too faint and too distant for direct observation. The foreground object magnifies these weak signals, bringing them into view. This magnification is not uniform. Different regions of the lensed image are magnified to varying degrees, allowing astronomers to resolve details within the distant galaxy that would otherwise remain hidden. We can study the birth of stars, map the distribution of dark matter, and investigate the earliest epochs of galaxy evolution. The principal mirrors that which creates the photon sphere around a black hole, the curvature of spacetime. Greater mass equates to greater curvature, and thus a more dramatic lensing effect. The photon sphere represents a most extreme manifestation of this phenomenon, according to theory. This bending of light is not confined to black holes or galaxies. It is a pervasive effect throughout the universe. Every massive object, from a single star to a vast galaxy cluster, subtly distorts the light that passes near it. It is a constant, subtle reminder that our perception of the cosmos is not direct, but always filtered by the gravity that governs all things. But if gravity can so profoundly distort what we see, what fundamental aspects of the universe remain obscured, waiting for a new form of detection? A fundamental contradiction exists at the heart of the cosmos. The more we learn about the universe, the more we discover its inherent limits. We have constructed telescopes capable of perceiving across billions of light years, instruments sensitive enough to detect the faintest echoes of creation. Yet, even with such extraordinary technology, definitive boundaries to knowledge remain. A black hole's event horizon represents one such boundary. It is not a physical barrier, but a point beyond which return is impossible. Crossing it does not involve being pulled by a force, but rather witnessing spacetime itself collapsing inward at a velocity exceeding that of light. Information, as we currently define it, cannot emanate from within. This presents a deep puzzle. Quantum mechanics postulates that information cannot be utterly destroyed. However, in the vicinity of a black hole, it appears to vanish. Scientists grapple with this conundrum, referring to it as the information loss paradox. Theories, intricate and as yet unproven, attempt to reconcile these seemingly opposing principles. What exists beyond the event horizon remains concealed from our view. Even if we dispatched a probe, any signals it transmitted would be irrevocably trapped. We cannot directly observe the singularity at the black hole's core, the point of infinite density where the established laws of physics cease to function. Our understanding of this region remains theoretical, constructed from mathematical models and extrapolation. The photon sphere, however, provides a fleeting glimpse of the extreme conditions immediately surrounding this boundary. Light, profoundly bent and warped, traces the contours of spacetime. It generates the dark shadow visible in images captured by the Event Horizon Telescope. That shadow is not the black hole itself, but the absence of light, the silhouette of distorted spacetime. It is a negative space, a void sculpted by intense gravity. This bending of light is not simply a visual phenomenon. It fundamentally alters the information we receive. Light escaping from the region around a black hole is stretched, distorted, and occasionally multiplied. It is as if the universe deliberately conceals its own secrets. We are compelled to assemble an incomplete picture, relying on indirect observation and sophisticated theoretical modeling. The universe does not surrender its truths easily. There are inherent limits to what we can observe, to what we can comprehend. These limits are not merely a matter of technological inadequacy. They are woven into the very structure of reality. The distortion of light around black holes is more than a spectacular visual effect. It is a window into the fundamental nature of existence. It serves as a potent reminder that our perception of the universe is always filtered, always incomplete. But if information truly cannot be destroyed, where does it go? A photon does not travel in a straight line. It traverses the curves of the universe itself. Space is not emptiness. It is a dynamic network, interwoven with gravity, and light invariably follows these connections. The most distant galaxies emit light that has journeyed for billions of years across expanding space. This expansion stretches and alters that light. The message we receive is not a present-day snapshot, but a relic from the past, molded by the evolving fabric of spacetime. Gravity, as Einstein demonstrated, is not a force acting upon objects. It is the curvature of spacetime caused by mass and energy. A massive object does not pull. It creates a depression, a dimple in the very structure of reality. And light, along with everything else, follows these curves. This is not merely a refinement of understanding. It is a fundamental shift in how we perceive the cosmos. To comprehend the universe, we must comprehend gravity, not as an unseen force, but as the geometry of existence itself, the way space is shaped, the way time flows. The bending of light is not a curiosity. It is a direct consequence of this principle, a visible manifestation of cosmic order. The photon sphere around a black hole represents an extreme case where light can orbit in captivity. But this principle operates everywhere. Even on smaller scales, light from distant stars bends as it passes near massive galaxies. This gravitational lensing distorts images, magnifies objects, and can even create multiple reflections of a single source. It allows us to observe objects otherwise hidden from view. Every observation we make is subject to this bending. The images we capture, the data we analyze, the information we receive from the cosmos, all are filtered through the warped geometry of spacetime. We do not see the universe as it is, but as it appears, sculpted by gravity. The 1919 Eclipse confirmed a prediction. The Event Horizon Telescope revealed a shadow. But these were merely glimpses of a more profound truth. We are each a small component of this vast structure, a fleeting moment within the immensity of time and space. Yet we possess the capacity to understand the laws governing this universe, to unravel the mysteries of gravity and light, to perceive the beauty and elegance of the cosmos. To realize our perception of reality is so intimately connected to the forces shaping the universe is a humbling experience. To understand that the light reaching our eyes has traveled for billions of years, bending and warping along the way, alters everything. The universe we observe is not merely a collection of objects, but a dynamic, interconnected web of spacetime. But if gravity so fundamentally shapes light, and therefore our view of the universe, how can we be certain we are not seeing an elaborate illusion?